Okay, this time we are required to calculate a multiple regression model. We have here two equations, and just we are going to do it right quick. The first thing we have to do before doing anything is just taking our equations and let's write them in its structural way of a system, of a multiple system of equations, is writing the equations in this way. Capital B times capital Y plus capital gamma times capital X equal to the error term. The capital B is the matrix associated with the endogenous variables. As you will see here, there are two endogenous variables, y1 and y2, and capital gamma is the matrix of the betas, in this time the gammas, that accompany every of the exogenous variables. We have three exogenous variables in this model, x1, x2, x3 namely, and as I've said, the better way to solve this problem is just put it in its general way. So to do that is just transposing terms to the left hand side of the equation, like this: 1 minus beta y2, 1 minus beta 2, 1. This would be the capital B matrix, times y1 and y2, the endogenous variables of the system, plus the gammas, less gamma 1, 1, less gamma 1, 2, 0, 0, 0, less gamma 2, 3, this is capital gamma, times x, x1, x2, x3, these are the exogenous variations of the system, equal to the error term in the equation number 1 and the error term in the equation number 2. These are stochastic variables, and as usual the error term in the first equation follows the normal with zero mean and constant variance, and the same for the second error term is distributed as a normal with zero mean and constant variance also. So how we do that? Let's clear this. To do that, just what we need is first of all clearing the y variable from this equation. How we do that? Just multiplying the whole system, both sides of the equal, by capital V inverse. Because this capital V would be cancelling this capital V, it could be an identity plus a vector is the vector, so this is the way of just clearing vectors in terms of matrices. So what we get here is just y plus capital V inverse plus capital gamma plus capital X would be capital B inverse times the error term. And just passing this to the other side of the equation, this, just to clear y, then what we get is that y would be less capital B inverse times gamma times X plus the error term. And we can call it, this operation of matrices, we can call it a new matrix called P, in fact. What this is giving us is this, E equal to P times X más this variable, multiply this error term, is giving us a new error term, call it V, for example. And this is an ordinary least squares estimation, if you see. Why? Because we got in the left hand side only the dependent variables, and on the right hand side only the exogenous variables. So this is an ordinary least squares estimation. The problem with this estimation, the problem with this P matrix, is that these P are biased and are also inconsistent, and in the short term and in the long term. And the reason why is because over here, this is the same as this, there are linear dependencies between the perturbations, between the error terms. So this is just disrupting our hypothesis that the new variable form has to be mean zero and constant variance, because it would be appearing covariances in this matrix, in the matrix of variance and covariance of V. So what I'm saying basically is that the expectation of V times V prime is going to be different from an identity matrix having constant variances in its main diagonal. So this hypothesis is being violated. So this is why the estimators of these ordinary least squares is not profitable for us. But in any case, is an aid for us. We're gonna see which type of aid. I need to clear in one side. Okay, let's clear here. Oh, let's clear everything. Don't worry too much. Let's clear everything. Okay, this was our equations. So we know that only the first equation can be estimated. We have collected a sample, and in this sample we got data. I don't know how many data, but what we have done is just to cross product the data in the cross product matrix. So all the information about the data has been collected in this crossed up matrix. And what we need to do, the first thing we need to know, as we have cleared the y variable from the system, is just calculating the ordinary least squares estimation. Because this would be the first stage of our true estimation, that is an indirect least squares estimation. So what we are going to do is evaluating this model. P11 x1 más P12 x2 más P13 x3 plus the error term, and for the second equation P21 x1 plus P22 x2 plus P23 x3 plus the second error term. So we are going to perform an ordinary least squares estimation over these betas, quote unquote, that are called p's. In fact, how do we do that? Using the equation for the ordinary least squares estimation. If you remember, for an ordinary least estimations, what we used is the Gaussian estimation. At this time we are using the Gaussian estimation. The estimation is performed multiplying the data, the matrix of data, capital X prime times capital X inverse times capital X prime plus y1 and y2, because this is a multiple model. So the estimation of the ordinary least squares would be x prime x inverse times x prime y1 and x prime y2. If you look at the cross products table, we can do that because the data is prepared to do that. Our x prime x matrix, if you look, is this 3 times 3 matrix that I have here. So this is just making numbers. P11, P12, P13, P21, P22, and P23 by ordinary least squares has to be this matrix 4, 0, 2, 0, 1, 1, 2, 1, 3 inverse times x prime e1, that is this vector, 3, 0, 2, and also times x prime times e2 times y2, that is this other vector, 2, 4, 1. If we do that, is what we take is the estimation of these parameters. If, let me remember, this was easy because the numbers are already arranged. This was 1/2 less 1/2, 1/2 for the first column, and the second column was 5/2, 8 and -4. So this is our ordinary least squares estimation. We use this ordinary least squares estimation as an aid to evaluate what we really are looking for, that is evaluating these betas and these gammas in the first equation. How we do that? How we do that? Again, if you remember, the structural model was capital beta times y, capital Y plus capital gamma times capital X equal to the error term. So it's transpassing these coefficients to the other side of the equation. This was 1 minus 2 beta 1 2 minus beta 2 1 1 times y1 y2 plus a minus 1 1 1 minus 1 gamma 1 2 0 0 0 minus 1 gamma 2 3 x1 x2 x3 equal to the vector of the error terms. Okay, and what we have done evaluating the ordinary least squares is we have estimated p, but p, if you remember, was minus capital V inverse times capital gamma. If you remember the equations, what we can do here is one thing. If I multiply both sides of the equation by capital B, what I get is that capital B times capital P has to be equal to minus gamma. So the way of evaluating this, we need to estimate capital B and capital gamma, these coefficients. The way of doing it is by this equation. So let's take this equation in mind, and also let's write again the capital P vector. Capital P was 1/2 minus 1/2 1/2 and 5/2 8 minus 4. This is our capital P. So as only the first equation can be estimated, what we can do is just, instead of having all the capital B matrix, just using the first row, because only the first row can be estimated. So what I can do is multiplying this by 1 and minus beta 1 2 at this side of the equation, and at the other side just taking the first row again of this structural model, but minus is giving us gamma 1 1 positive, gamma 1 2 positive, and 0. So the way of estimating these parameters by indirect least squares is just performing this operation that comes from this relation, right? So let's do it right quick, just to finish the problem. So what we know, okay, if let's start by the beta, taking advantage of this 0. If I multiply this vector by the last column, what we get is 1/2 positive for beta 1, 2 has to be equal to 0. So 4 times beta 1, 2 has to be equal less 1/2. So beta 1, 2 has to be less 1/2 over 4. That is to say, less 1/8. So we have complete our first estimation. This is the beta estimation using indirect least squares. For the rest of the group, we can do the same. Let's begin with first row by first column. What we know is that 1/2 minus beta 2, 1 times 5/2 has to be equal to gamma 1, 1 minus, as we have already estimated beta, this is minus 1/8. We can substitute it here, and minus 1/8, what is giving us is 13/16. And for the second, if we multiply this row by this column, then minus 1/2 minus beta 1, 2 times 8 has to be equal to gamma 1, 2. Again, as beta 1, 2 has been already estimated, is less 1/8. This term becomes positive. 8 divided by 8 is 1. 1 less 1/2 is 1/2. So we have completed our estimation successfully. So what we can say now is that the estimation of the first equation is gamma y1 t by indirect least squares has to be equal to minus 1/8 y2 t plus 13/16 x1 t plus 1/2 times x2 t. And this is our equation estimated in a right way. It can be seen that these estimators, the indirect less estimators, in the long term are consistent, whereas in the short term they continue to be biased, but it's okay. Okay, that's all. Thank you for having me this time. Bye bye.